All right, let's jump right in. Today, we're talking about one of the most critical parts of professional machine learning, and that is reproducibility. And look, this isn't just about having good habits. It's really the foundation for building ML systems that you and everyone else can actually trust.
It's the worst feeling, right? You have that amazing breakthrough. The model's metrics are off the charts. You think you've finally cracked the code, and then the next day, poof, it's just gone. It's like a ghost in the machine that you just can't bring back.
I'm guessing if you've been working in ML for any amount of time, you're probably nodding your head right now. It is such a common and honestly a soul-crushing problem that can bring a whole project to a grinding halt.
But here's the good news. If this has happened to you, you are definitely not alone. And even better, there's a clear, systematic way to fix it. So today, we're going to lay out the exact framework to make sure this disappearing model problem never happens to you again.
So let's give this thing a name, this enemy. We'll call it the disappearing model problem. And honestly, solving this is what separates messy data science projects from professional, scalable ML engineering.
So, where did it all go wrong? Well, it's almost never just one single thing. It's usually a bunch of small things. Maybe the training data got updated without you realizing it, or a tiny little tweak was made to the code. Maybe your Python environment is just slightly different from your teammates. Or, and this is a classic, a random seed wasn't set, or you just can't remember the exact learning rate you used. Each one is a tiny leak, but together, they sink the whole ship.
And the fallout from this, it's huge. I mean, if you can't reproduce a model, you can't debug it, you can't deploy it with any confidence, and you certainly can't explain how it works to a stakeholder or an auditor. It just completely shatters trust in your work and in the entire system.
Which brings us to a really crucial question. Why should you even care this much? Well, because reproducibility isn't just some nice-to-have best practice. It is the bedrock of building trustworthy machine learning systems.
And at its heart, the definition is super simple. It's just the scientific method, but for ML. It means if I take your code, your data, and your exact setup, I should get the exact same result. No surprises, every single time. Now, I know what some of you might be thinking. Okay, but is all this control really necessary? Isn't a model that's good enough okay? Well, let's talk about why the answer to that is a hard no.
Yeah, it's not optional. It is absolutely mandatory. You need it for debugging. I mean, how can you fix a problem if you can't even make it happen again? You need it for auditing, for compliance, especially if you're in an industry like finance or healthcare. You need it for reliable deployments, and you for sure need it to collaborate with a team. Without reproducibility, you're not doing engineering, you're just guessing.
Okay, so how do we do it? How do we actually get there? Well, it's not magic, it's just good, solid engineering. And we can bring order to all this chaos by following what we're going to call the pillars of control.
Okay, this is the whole shebang. The roadmap to sanity. We can break this down into 7 key pillars. First, experiment tracking, so you know what you did. Then, data versioning. Think of tools like DVC as Git, but for your data. You need configuration management, so your parameters aren't lost in your code. Environment reproducibility, using Docker or Conda, is crucial so everyone's on the same page with libraries. We need to control randomness with random seed control. Then, pipeline automation makes the whole process repeatable with a single click. And finally, a model registry to manage all the models you've built. Get these 7 right, and you're in total control. All right, enough with the theory. That all sounds great, but let's get our hands dirty and see what this stuff actually looks like in practice.
Let's start with an easy one that has a huge impact. Taming the chaos of randomness. You know, things like how your data is shuffled or how your model's initial weights are set. That's all random. If you don't control that, you will never get the same result twice, period.
And the fix for this? It is ridiculously simple. You just set what's called a random seed at the very beginning of your script. It's just a number, like 42, that tells all your libraries, like NumPy or PyTorch, to make the exact same random choices every single time. It's literally a few lines of code that solves a massive headache.
Okay, next up, and this is a big one, managing your configuration. Please, whatever you do, stop hard-coding things like learning rates or the number of layers directly into your Python scripts. That is just a recipe for disaster. Instead, you pull them all out into a nice, clean configuration file, like this YAML example here. This totally separates the what from the how. This little file can now be versioned in Git, you can share it with your team, and it gets logged with every experiment. Suddenly, everything you do is transparent and easy to repeat.
And finally, let's circle back to that first pillar we mentioned, experiment tracking. Because honestly, if you run an experiment and you don't log the parameters, the metrics, and the final model, did it even happen? It's like it just vanished into thin air.
This is where tools like MLflow come in and just save the day. With just a few simple lines of code wrapped around your training logic, you can automatically save everything about that run. The parameters you used, the final accuracy score, even the model file itself. It becomes your lab notebook, but one that's automatic, perfect, and can never get lost.
Okay, so let's bring all this home. We've talked about the problem, why it's so frustrating, and the tools you can use to fix it. Now let's put it all together into a really simple, actionable blueprint that you can start using, like today.
At the end of the day, it really comes down to a choice. There are two paths in front of you. On the left, you've got the path of professional discipline, version data with DVC, clean configs, tracked experiments, automated scripts. It's reliable. And on the right, well, that's the path to chaos. It's filled with files called final_v2.csv, untracked notebooks, and forgotten settings. The choice is pretty clear.
I want to leave you with this one last thought, because it really changes how you look at everything. A model isn't just that final .pkl file. A model is the entire process that created it. And if you can't reproduce that process, you don't really have a reliable, engineered asset. What you have is a lucky accident. And reproducibility is what turns those lucky accidents into real engineering.